Four objects are on a 2-meter long rod. A fulcrum is placed directly in the middle of the rod. A 5 kilogram box is 50 centimeters to the right of the fulcrum. A 3 kilogram box is 60 centimeters to the right of the fulcrum. A 4 kilogram box is 90 centimeters to the right of the fulcrum. How much force needs to be applied 80 centimeters to the left of the fulcrum to prevent the rod from rotating? So, to solve this problem, starting off with a diagram of what the situation looks like is going to be recommended. So I'm just drawing this rectangular shape with graduations on it. That is going to represent my rod. Directly in the middle of it, I'm drawing a triangle to represent a fulcrum. Right now, it looks like the object is balanced, and that would imply that the object is not rotating. I'm adding a scale here. I am setting that fulcrum as a position of 0. That way I have 100 centimeters to the right and a 100 centimeters to the left. This allows me to have that reference point of 0 be dead center of my diagram, and then I have 1 meter to the left and 1 meter to the right. Now I can change that reference of 0 if I want, but considering I have some number of centimeters to the right and some number of centimeters to the left, it makes sense to have my center point be 0. The 5 kilogram box, which is represented with this gray box with number 5 in it, I placed at the 50 centimeter mark to the right of the fulcrum. I'm doing the same thing with a 3 kilogram box at the 60 centimeter mark to the right of the fulcrum, and then the same thing with the 4 kilogram box, 90 centimeters to the right of the fulcrum. I don't know how much force is necessary, nor do I know the mass of the object, but I do know the location of it, so I'm putting an unknown object at a position of 80 centimeters to the left. This right here is the diagram. Because we are solving for force, I'm going to start off by constructing a force diagram. Now, because we have this object that could potentially rotate, I'm not going to be treating it as though we're looking at a particle representation of our entire system, this being our system. Instead, I'm going to go with a simplistic approach where we can talk about the forces applied where on the object and how that can contribute to the potential rotation of the object. So to do that, this rod is a rectangular shape. So a nice simple shape to represent for a force diagram would just be a rod. I'm drawing the rod right here. The first force I'm going to draw directly on the rod is going to be the force of gravity. Now I'm going to draw the force of gravity originating at the center of mass of our system. Now, we can make the assumption that this object has uniform density, so that means that the dead center of this object is where the center of mass should be. So I have a force gravity pointing down. We're not told the mass of the rod, so we don't know exactly how big to draw this force gravity. So I'm just going to say there is some force pointing down. That's the force of gravity. It originates at the center of mass. Then I need to see what else is interacting with my system. Well, I know that 5 kilogram mass is on top of our system, so it will be exerting a downward force. Now notice, I'm not drawing that force at the center of our system. I am drawing it to the right. That is going to be where on our system that force is applied, force 5. I'm doing the same thing with force 3, and the same thing with force 4. Just like in our previous model of how we drew our force diagrams, the length of each force vector is proportional to the magnitude of the force. Now, I can't say anything about the magnitude of the force gravity. That was arbitrary because we don't have any indication of how big that force vector should be. However, I know force 5 is going to be proportional to the mass of that object, which is greater than the mass of the 3 kilogram object, which is why the force vector is longer. And then our force 4 is somewhere in between the two. So, once again, our force vectors should be to scale. We have another force. That is that unknown magnitude of the force, 80 centimeters to the left of the fulcrum. Now, I'm just drawing this in arbitrary length, but we can scale it later on after we know the actual magnitude of the force. But we can draw it here because we do know that it is going to be on the left of our system, which is where our force needs to be applied. So we have the 4 downward forces from each of those 4 objects on top of our system exerting a downward force. And we have that force gravity pulling down on our system. We have the fulcrum underneath our system. It is exerting an upward force on the center of our system. Now, I'm going to be saying that if the system is not rotating, it is also not accelerating in any direction. That means overall, all of the forces need to be balanced. So I'm drawing that force normal as though it would balance out all 5 of those downward forces, which is why my force normal looks so large. There are no other objects interacting with our system, so we have no other forces that we need to represent on our force diagram. So at this point, we can write the force summation equation. We have no horizontal forces, so our only forces that we need to include in the summation equation are our vertical forces. So our sum of our forces would be equal to the upward normal force minus all of those downward forces, the unknown force plus the force gravity plus the force 5 plus force 3 plus force 4. And then because our system as a whole is not accelerating, the net force on our system is 0. In the past, when we've been calculating how much force we need to solve for, we have used our summation equations to do that. We can rewrite our sum of the forces in the ways that we can quantify our forces. We don't know what the force normal is going to be. We don't know what the unknown force is going to be. But we can calculate the force gravity of our system as the mass of the system, in this case the mass of the rod, times our gravitational acceleration. We know that if the system's not moving, then the force applied by force 5 would be its normal force, the normal force on the system by force 5. And then, if we were to draw a force diagram for box 5, box with a 5 kilogram mass, you just have 2 forces, force normal up, force gravity down. That system itself is not accelerating, so we can quantify the force gravity and the force normal with mg, which is why we can say that force 5 applied to this system is the mass of the 5 kilogram mass times our gravitational acceleration. We can do that with force 3 and force 4. And then overall, it adds up to 0 newtons. While we can quantify quite a bit of this equation, G, M4, G, M3, G, M5, G, and we don't know the mass of the rod. So we can't actually quantify this part of it. We can't quantify this, nor can we quantify this. As of right now, we have 3 unknowns, and we are trying to solve for one of them. But because we have 2 other unknowns as well, this approach is not going to allow us to solve for what the problem's asking for. This is where we need to bring that new concept of torque. We're going to need to write a torque summation equation for this force diagram. Now to do that, we need to identify that pivot point, or that axis of rotation. Now, because this object is ideally not rotating, we don't actually know for a certain where to place that pivot point. However, we can make the assumption that if there's a fulcrum here, presumably the rotation is going to be about that fulcrum. And then also it has the benefit of helping to simplify our torque summation equation, which we'll talk about in just a second. But right now, I have drawn on my force diagram this open circle that represents our axis of rotation, or the pivot point of our system. But before I can write the torque summation equation, we need to review what torque is going to be. We can quantify the torque, any individual torque, as the perpendicular component of force, multiplied by the distance away from the pivot point. Now that perpendicular component of force is the force that is perpendicular to the radius. So what we're going to need to do is we're going to need to identify any relevant angles on our force diagram. And if any of those forces are not perpendicular to the radius, then we would need to quantify how big that perpendicular component is. So, fortunately for this one, it looks like every single force, all 6 of them, are perpendicular to the rod. And then the rod in this case would be the axis along which we have our radius, or that distance away from our pivot point. So we don't need to worry about doing any trig to figure out the perpendicular components of the force. We just need to identify which of these forces are some distance away from the pivot point. The unknown force is going to be 0.8 meters away from the pivot point. The force 5 is 0.5 meters away from the pivot point. Force 3, 0.6 meters, and force 4, 0.9 meters. we don't have an R value for the force gravity or the force normal because the distance from here to here is 0. If this right here is our axis of rotation, that pivot point, neither the force gravity nor the force normal will cause a torque on our system. So that unknown magnitude of force gravity and that unknown force normal goes away in our torque summation equation because both of these produce 0 torque. Now, before we actually write the torque summation equation, there will be one more thing we need to define. Which direction is positive? The unknown force, if this were the only force on our system, and it's still pivoting around this point, would pull down on our system, and it would cause a counterclockwise rotation of the rod. Force 5, force 3, and force 4 would cause a clockwise rotation of our system. These are rotating in opposite directions. We need to define which way is going to be positive for our purposes. We have three torques that are clockwise and one torque that would be counterclockwise. To simplify the math as much as possible, we'll go with the more abundant direction being positive. So for our sum of our forces, we have a negative torque from that unknown force. And then we have a positive torque from force 5, a positive torque from force 3, and a positive torque from force 4. All of those will sum up to a net torque of 0 Newton meters. Our system starts off not rotating, and it continues to not rotate. So our net torque should be 0. Now we can also rewrite our torque summation equation in a way that makes it easier for us to solve for the force. Because if each individual torque is the perpendicular component of force times the radius, we can write each of those torques as their force times their radius. This right here would be the torque summation equation in relation to this force diagram with this pivot point that we have identified. But you might notice that this force diagram is kind of messy right now. Honestly, when we're constructing it, all we really need to represent is a simplified representation of the system, in this case, that thin rod, where the axis of rotation or that pivot point is, any relevant forces, and then if we have any non-perpendicular forces, we would need to identify those relevant angles. Where I labeled the radii and then all of those right angles are unnecessary for the force diagram. If it helps to visualize exactly where everything is, have a working force diagram and have the clean force diagram to kind of separate what you're presenting and what you're actually working on. But now that we have this torque summation equation, we can use it to actually solve for the problem. So to do that, I'm going to take that version of our net torque equation, where we have our forces and our radii that sum up to 0. Just simplifying it so that way we don't have net torque equals anything. It's all of those individual torques sum up to 0 Newton meters. I rearrange the equation to get our unknown force by itself. Right now it's just our unknown torque. But to get the unknown force by itself, I can just divide both sides by that radius that we were provided with for that unknown force. It's that radius of 80 centimeters to the left of the fulcrum. I can rewrite each of those three forces here as mg. And then at this point, we have a format where our unknown, the thing we're solving for, is isolated by itself on one side of our equal sign. And on the opposite side of the equal sign is a bunch of variables where we know the value of each of them. So I factored out the gravitational acceleration from the numerator up here, and then I plugged in the mass and the radius value for each of the three objects to the right of the fulcrum. So the 5 kilogram mass times the 0.5 meters for the radius, plus the 3 kilograms of mass times the 0.6 meters of radius, or the distance from the pivot point, plus the 4 kilograms of mass times the 0.9 meters of distance from the radius. And I divide that all by the distance to the left of the fulcrum. When we simplify this down, the force that would be required to prevent our system from rotating would be 96.775 newtons.